Cool. I'll begin now. Um, Hi. Um, Good evening. Eli Bacus. Thank you for taking the hour at the end of your day to listen to my building sciences capstone presentation on my American carbon policy proposal. I do have a 40-minute time limit, so I'd like to keep it as one recording. So I do ask to keep all questions till the end. Um, so This project is made up of four sections. First, I'll introduce my project with the current United States climate goals, national progress, and my initial study. I'll then go into a case study, my initial policy, simulated models, then a newly proposed zoning policy. So in April of 2020, the Biden administration announced a national goal to reduce the economy-wide greenhouse gas emissions by at least 50% from levels recorded in 2005, with further goals to reach a net zero emissions economy by 2050. However, even with current policies like the IRA, as of 2022, the US has only achieved about a third of its 2030 target. According to projections by the Climate Action Tracker, an additional 30 to 44% of that goal will be met by 2030, but still fall short by 23 to 37%. With that, many studies and projections see our progress as insufficient and point towards further policy action as one of the most impactful ways to close that gap and reach our national climate goals. So earlier this last year, during my internship at Rensselaer, I was motivated to propose a policy within the building industry that would help further close that gap by taxing embodied carbon in building materials. Since I have limited time, I'll give a brief summary and expand on my initial proposal later in the Q&A portion. Um, my proposal was built upon existing federal greenhouse gas emissions reporting policies so that manufacturers were required to track and report their greenhouse gas emissions annually to the EPA. Each state would then tax the manufacturer for their in-state emissions equivalent to the cost of carbon offsets credits required to offset their emissions and claim net zero compliance. This would essentially be an excise tax for building materials that produce embodied carbon. So materials that were more carbon intensive to produce had a greater additional cost compared to materials with lower embodied carbon. My goal was to incentivize consumers like property owners and developers to choose materials with lower embodied carbon. And I applied this on different wall systems ranging from a low EC to high EC assembly and found that although the assemblies with higher embodied carbon had higher additional taxes, it was not significant enough to prioritize over factors like R value, thickness, and availability. Now, what I took away was that there were so many problems with my methodology and application of my policy. First off, the use of offsets. Although cheap at an average cost of $12.25 per metric ton, there are a lot of questions concerning measurability, verification, and risk of default, which led me to look towards projects with better abilities to track and report capacities like carbon dioxide removal technologies. Another problem was inaccurate projections due to immediate implementation. With the introduction of a policy, the demand greatly exceeded the supply of projects within the country, inflating the price. This would be further amplified if I decide to switch my focus towards carbon dioxide removals capacity, which do have a significantly less volume compared to offsets. So by proposing new policy now and implementing later around 2030, this gives the opportunity for supply to at least catch up and have a little bit more accurate projections. So moving on to last semester, I wanted to revise my initial proposal and pivot investment towards carbon dioxide removal projects. I'll briefly summarize some CDR methods, so carbon dioxide removal, CDR, in the United States, as well as why I chose to invest in certain methods over others. And later on in the presentation, I actually revisit this methodology. So here you'll see a map of carbon dioxide removal projects federally funded by the Department of Energy across the United States. 45 of those projects are direct air capture and 8 are marine-based capture. Now before I continue, I'll briefly expand on Before I briefly expand on various removal methods, it is important to know that carbon dioxide removal involves removing CO2 from the atmosphere and storing it safely in geological, terrestrial, or oceanic reservoirs. This is different from offsets, as offsets compensate for emissions by balancing emissions elsewhere. Another important concept to understand is permanence. This refers to the storing durability of CDRs projects. So a low permanence would be decades to 200 years, and a project with high permanence hold um, would have a durability of millennia to millions of years. Now, the barriers concerning CDR, which makes it less appealing compared to offsets currently in the market, are its difficulty to scale and initial startup costs, which are very high. Carbon removal credits range from $25 per metric ton to $1,000 per metric ton of CO2 equivalent removed. For CDR, there are three categorical methods in which carbon dioxide is removed and stored, first being a natural method. Projects under this method, like afforestation and soil sequestration, leverage natural processes to capture and store atmospheric CO2 without significant technological intervention. These generally cost less than other methods. However, permanence varies from decades to centuries and is low relative to the other two methods. But the reason I chose not to focus on natural methods for now, this first half of the project, is because of the challenges of verification requiring more effort and innovation for monitoring. Next is hybrid methods. These methods combine natural processes with technology for CO2 capture and storage. These approaches leverage both nature and innovation. So these typically cost between $150 to $600 per metric ton. Permanence varies between these projects depending on environmental factors. Monitoring and verification also varies between easy and medium depending on project type. The final category is engineering methods. These methods rely on human-made technologies to actively capture CO2 from the atmosphere or oceans and store it in stable forms. These approaches are more technologically advanced, offering precise control and higher potential for scalability. Oh, whoa. These cost upwards of $150 per metric ton, more closely between $600 to $1,000. These projects also have the highest permits and little to no risk of defaulting compared to the other two methods. Removal capacity can also be easily tracked and verified, and these factors make it desirable since engineered methods are measurably precise, scalable, and highly durable as a solution for sequestration. So now instead of allocating tax revenue towards offsets, my revised policy will allocate taxes on embodied carbon as well as operational carbon towards engineered CDR projects in the United States for this half of the project. I'll quickly highlight two direct air capture projects currently operating in the United States. First being Global Thermostat, based in Colorado. Since 2022, they operate one of the largest direct air capture machines in the world with a capacity of 1,000 metric tons of CO2 per year, called the K series. The next is Heirloom out of California with their own 100 metric ton facility that's been operating since 2023. What's really cool about Heirloom is that along with their carbon capture, they also inject carbon into concrete, which is used for non-structural applications like sidewalks. They both have future proposals for larger facilities with increased capacities. Heirloom with a 320,000 metric ton facility proposed in Louisiana, and GT with their M series facility aiming to have a capacity of 1,000 metric tons, which is already receiving funding from the Department of Energy. Both aim to reach full operational capacity before 2030. As for New York State, the GE Cage Lab in Schenectady County is developing a direct air capture system that also aims to minimize energy use. So they've conducted larger scale trials in 2024 and should be commercially viable by 2030. They aim to be more cost effective compared to other DAC projects around the country, and this project is also funded by the U.S. Department of Energy. And another company called Vicarb out of Brooklyn has a direct ocean capture system that removes 100 metric tons of CO2 annually per unit while addressing ocean acidification. The autonomous and scalable system uses real-time monitoring for accurate CO2 removal and storage with an operational cost of under $100 per metric ton. And it future plans wants to scale it to larger um, systems with larger capacities with projects in New York and Massachusetts. Okay, now on to the policy. First part of my policy. My initial proposal for an operational carbon tax for property owners would start with site energy use. I'd multiply that by a percentage of non-renewable grid energy sources. For New York State, 76.25% of grid energy comes from non-renewable sources. Then I'd subtract the amount of on-site energy generation and purchase RECs to get the total taxable energy use. That would then be multiplied by the state emissions factor, which for New York is 0.199 in order to get the taxable emissions quantity for that site. That would finally be multiplied by the carbon removal rate, which is the cost of removal per kilogram of CO2 equivalent through projects within the state. And the key goal with this policy is for builders and property owners to increase investment into low energy designs and in systems and increase their on-site energy generation. And for local governments to increase renewable energy sourcing, such as hydropower, solar power, wind, etc., and decrease their carbon removal rate by increasing volume and project investments towards carbon dioxide removal projects. So I'll apply this to a site. I chose a site in downtown Troy. It is 102 First Street, Troy, New York. It is in climate zone 5A. It is a 9,600 square foot lot. It's going to be a new build, 3-story building with a basement, 3 units, each with two beds, 1 bath, and a kitchen. And a highlighting feature is in the baseline model, will be a 8-inch brick facade. So here is a Rhino model, expanded Rhino model of the site. It'll have the ICFA of 8,610 square feet. It'll have code minimum R values. It'll have an annual site energy use of 89,242.4 kilowatt hours per year and have 0 on-site energy generation. And you could see large amount of energy use towards space heating there. 40% of the building's volume is masonry, 39% is insulation, and 20% is timber, and 1% is in additional materials like windows, etc. And using EC3, Excel, capturing volumes and square footage on through Rhino and using EPDs, the total embodied carbon of the material was about 164,936 kilograms of CO2 equivalent. 41% of that coming from the structural brick wall, which had an EC rate of 14.24 kilograms of CO2 equivalent per cubic foot. Other high contributors were the concrete substructure and the high quantity of fiberglass bat insulation used within the wall assembly. So to calculate overall cost between the years 2030 and 2050 of this baseline model, I took some cost projections from various studies. First being energy cost, I used projected grid energy price of the New England region from the U.S. Energy Information Administration. I chose New England because it more accurately resembles upstate New York's energy prices. Next were projected carbon removal prices per metric tons, starting from 2030, as well as offset credit prices for comparison. Data was sourced from the 2024 Bloomberg NEF published studies. Lastly, a few more figures used in the calculations. Construction costs from materials listed was 2.15 million. Usually using as much locally sourced material as possible. I'd say this was the most difficult part, just trying to find a baseline cost of materials. We didn't hard time estimating labor, I would say, in this process. New York State's greenhouse gas emissions, according to a carbon footprint study in 2023, was listed as 0.199. And upstate New York's non-renewable grid energy was 76.25% as of 2023, according to New York State Comptroller Report. Embodied carbon data was conservatively chosen from EPDs available on EC3. If you want to know how I did that, you can ask me later. And lastly, the energy use calculations was done through Wufi. With that data, the total cost of carbon removal tax for the baseline model between 2030 to 2050 was $97,318, with $14,500 covering the cost of embodied carbon and $82,639 covering the operational carbon. You'll see the green line is the removal tax rate, and then with the removal tax rate, and the orange line is with the offset tax rate, just for comparison. Now for the cumulative cost with construction and energy cost added, the baseline model would cost a total of $2,817,892 under the carbon removal policy. And the carbon tax represents only a few percent of the total cost of the building in both scenarios. However, when combined with the projected cumulative cost of energy, it becomes very significant. For example, in the removal scenario, it's almost 25% of the total cost. So as a property owner, long-term costs begin to factor into early design decisions and efficiency goals. But now with the extra carbon removal tax, addressing long-term energy costs can also address tax payments, the incentivizing owners and developers to look into alternative measures and materials or systems. With long-term costs of energy and carbon removal tax in mind, we can begin to see built proposals to the site that could look like this. So improvements to the building envelope could be made using materials with lower embodied carbon. For example, addressing the carbon intensive wall assembly for the baseline model using a brick veneer instead of an 8-inch structural brick facade was pretty easy design choice. And replacing conventional insulation with natural insulation like wood fiber wherever possible. Along with these changes, improvements could be made to the building's thermal envelope, increasing R values in the walls and ceilings and upgrading the windows. So when I compare the embodied carbon between the baseline model and the updated model, we can see a significant decrease from 165,000 kilograms CO2 equivalent to 105 kilograms of CO2 equivalent, with a large reduction coming from substituting that brick wall in the wall assembly by substituting insulations like fiberglass in the walls and cellulose in the ceilings to locally sourced wood fiber. There wasn't only a reduction in embodied carbon values, but also a carbon sequestration quantity that also came along with it. However, additional embodied carbon was also taken in with the upgrade of the windows and implementation of PV panels on the roof. But you'll see in a couple of slides the humongous payoff that on-site energy generation offers. In the updated model, I also switched to an all-electric heating and cooling system with the use of a geothermal heat pump. And like I said previously, the addition of PV panels, which generate almost 42,000 kilowatt hours per year. These changes result in a decrease of site energy by almost 50% from the baseline to the updated model. And with the PV panels generating 93% of that energy, it leaves the building with a net annual load of 2,921 kilowatt hours per year. This reduces about 445 kilograms of CO2 equivalent per year, which again is a significant decrease from the baseline model, resulting in a total removal tax of $11,430 over a 20-year period. Energy costs also decrease to $14,612 over 20 years. And when cumulative costs are compared, even with the increase of 10% in construction costs for the updated model, it is still a significant decrease in costs compared to the baseline model. So now that I have the initial site portion of my policy where I'd like it to be, what about the allocation of tax funds? So to visualize the allocation of funds under a carbon offset policy scenario, I'll use afforestation and the baseline model as an example. So according to studies, did I not? Yes, I listed the source. According to studies, 1 acre of native and mature red and white pine, the native to the Northeast United States, sequesters about 4,500 kilograms of CO2 equivalent annually. Um, in order to sequester the amount of embodied carbon produced for all the materials in the baseline model over the course of 20 years, you would need to plant 1.83 acres of trees. And for the annual operational carbon, an additional 3.89 acres, which results in a total land use of 5.72 acres. However, even then, we would need to wait till all these trees reach maturity in order to even achieve the reported annual removal capacity, not to mention the lack of land. Now, in a removal scenario, using the direct ocean capture unit from bicarb that I mentioned earlier, the site would only use 14% of the unit's removal capacity to cover the operational carbon. And the entire unit would cover about 18 of the surrounding residential units at full removal capacity. However, if you were to remove the operational carbon from all the residential units in this small portion of downtown Troy, you would need about 958 individual bicarb units, or just one future GT series facility that doesn't exist yet. So with that, I find myself with a problem in the methodology for my tax allocation. The concept of relying on engineered methods isn't flawed only because isn't only because there's just too much demand, causing it to be much more expensive and breaking the projections. It is also unethical to invest in projects that would build these facilities for almost every urban municipality in the state, not to mention New York State, which has a city like New York City on land that, although unused, has contributed towards the ecosystem and most likely already acts as carbon sinks. So I'm forced to look back at the diagram of removal methods with these new questions and find a way to, one, find additional supply for removal demand, and two, which is now the priority, protect existing natural infrastructure. If municipalities can identify carbon sinks within their jurisdictions and conservatively measure their carbon removal capacity, it can be the primary method of carbon removal. Carbon sinks like public parks, protected forests, publicly funded farmland, etc. By allocating carbon tax revenue towards the maintenance and or enhancements of these carbon sinks, a zoning policy can be made to protect these natural methods in order to claim their contribution towards overall carbon removal. Engineered methods like large direct air capture facilities can then be used as a supplemental method that a state or municipality can use in order to meet their net zero targets. Zoning can also be used to identify and protect areas with potential to have carbon dioxide removal projects like vacant lots or open grass fields. This would be important towards long-term planning. So this will now lead me to my zoning policy. So if we look back at the map of downtown Troy around our site and start with the site itself, property owners can add and enhance their natural carbon removal capacity by planting and maintaining trees, incorporating additional plants, farming, composting, and claim sequestration capacity within their property. In the future, maybe appropriately sized CDR technology could even be implemented to contribute towards on-site sequestration. And these are all big ifs into the future if we're able to even account for these methods and quantify them and report them. And if municipalities can recognize capacity on private properties and add to their supply of removal capacity, a strong argument can be made for tax subsidies for these property owners. But the main part of the zoning policy can be identifying areas with existing natural removal capacities and protecting it in order to measure, maintain, and claim their carbon removal potential. For an urban area like downtown Troy, these are parks with mature trees, open grass fields, and urban farms. For rural areas, which I'll show an example of in a few slides, this can be protected forest and farmland. Then the maintenance, enhancements, and tracking operations of these areas receive primary allocation of the tax revenue. Another part of the zoning policy is identifying opportunities to use carbon sequestering and carbon materials in municipal infrastructure, like biogenic asphalt for roads, carbon injected concrete for sidewalks and parking lots. Next is the zoning policy can also include protecting areas with potential to become sites of carbon dioxide removal projects, like vacant lots or open roofs. This can also extend for opportunities to enhance the sequestration potential of existing infrastructure, like improving the soil in an open field that doesn't necessarily have the health that it once yielded as a carbon sink. And even then, you may say that this still isn't enough to address the removal demand of downtown Troy. But where it all balances out, when you move a couple miles downstream to the area just above the southern border of Troy and use the exact same mapping exercise at the exact same scale, you can find the balancing supply of carbon sequestration. So here, this is publicly owned land by New York State, a little bit of private up here in the northeast part of this map. So you can even identify larger areas of unused land away from residential units for a supplemental carbon dioxide removal facility. So here you'll see 100 acres of mature forests, which sequester 445,700 kilograms of CO2 equivalent per year. So in conclusion, my carbon removal policy is two parts. Site. So new builds are taxed relative to the embodied carbon produced by all building materials to incentivize low EC material procurement. Properties are taxed relative to their non-renewable energy use to incentivize efficient, low energy systems and designs, as well as on-site energy generation. This aims to increase renewable grid energy sourcing to lower and eventually diminish the carbon tax rate. Whoa, okay, running out of time. And then zoning. Areas with existing natural removal capacities are protected in order to measure, maintain, and claim their carbon removal potential. The maintenance and enhancements of these areas receive primary allocation of tax revenue. Areas with potential to become sites for carbon dioxide removal projects are also protected for long-term scalability. Engineered CDR projects are then granted allocation in order to meet the net zero targets as a supplementary method. And this aims to leverage existing carbon removal infrastructure, protect green spaces, and lower the demand and reliance on technological investment. Thank you for staying and listening. Cool. With 10 minutes left.
Thank you, Eli.